Somewhere in the darkness beyond our solar system, a machine built in the 1970s is still whispering back to Earth. Not loudly, not clearly, just a faint signal drifting across billions of miles of empty space. And recently, something strange appeared inside that signal, a pattern that should not exist, because Voyager was never designed to send anything like it. Which leads to a question that feels a little uncomfortable the longer you sit with it. If the spacecraft did not create the signal, then what did? There is something haunting about machines that outlive the people who built them. Voyager 1 was launched in 1977. Most of the engineers who designed its systems are now retired. Some of them are gone. The computers used to build the spacecraft would look ancient compared to what sits in your phone today. Yet Voyager is still alive, still sending signals back to Earth. And it is not just far away, it is incredibly far away. Voyager 1 is now more than 24 billion kilometers from Earth. It has crossed the boundary of the heliosphere, the giant bubble of charged particles created by our Sunday. Beyond that boundary lies interstellar space, the space between stars. A place so quiet and cold that sunlight becomes little more than a distant glow. Even radio signals take more than 22 hours to travel from Voyager back to Earth. That means every message we receive from the spacecraft left it almost a full day earlier. It is like listening to a voice from the past. For decades, Voyager has behaved exactly the way scientists expected. It sends engineering data, magnetic field readings, cosmic ray measurements, simple telemetry from instruments that were designed nearly half a century ago. But recently, researchers monitoring the signal noticed something odd. Something that did not match any normal spacecraft behavior. Before we go deeper into that strange moment, there is something important. Investigations like this take time, digging through spacecraft data, scientific papers, and decades of mission history. If you enjoy these kinds of deep space investigations, consider subscribing. It helps fund this kind of research into the unknown. Now here is where the story becomes interesting. Because Voyager is not just another spacecraft. It is the farthest object humans have ever built. And when something unusual appears in its signal, it gets attention. A lot of attention. Voyager 1 left Earth during a time when computers filled entire rooms. The spacecraft itself carries less computing power than a modern calculator. Yet its design was brilliant. Engineers at NASA's Jet Propulsion Laboratory built it to survive decades in space. It traveled past Jupiter in 1979, then Saturn in 1980. After those encounters, Voyager continued outward, riding a gravitational slingshot that pushed it toward the edge of the solar system. Along the way, its instruments recorded incredible discoveries. Volcanoes erupting on Io, complex rings around Saturn, strange magnetic fields surrounding distant planets. Each time the spacecraft sent back new data, radio antennas on Earth captured the signal. Those antennas belong to the Deep Space Network, 3 giant listening stations located in California, Spain, and Australia. Each one uses massive dish antennas capable of hearing whispers from billions of miles away. Without those antennas, Voyager would already be silent. Because the spacecraft transmits only about 20 watts of power, roughly the energy used by a small refrigerator light, yet across the vast emptiness of space, that signal still reaches Earth. Engineers at the Jet Propulsion Laboratory monitor Voyager's telemetry every day. Telemetry is the spacecraft's way of saying how it feels. It reports temperatures, power levels, instrument status, orientation in space. Normally, the information arrives in neat digital packets, numbers that computers decode instantly. But one day, those numbers stopped making sense. The spacecraft was still sending a signal, but the signal contained data that could not be decoded properly. Some numbers were wrong. Some patterns looked scrambled, yet the spacecraft itself continued operating normally. Its instruments still worked. Its power systems remained stable. That contradiction confused the engineers. If the spacecraft was healthy, why was the signal behaving strangely? At first, the team suspected a simple glitch. Old spacecraft sometimes experience memory errors. Radiation can flip bits inside aging electronics. So engineers began reviewing the telemetry logs carefully. They compared the strange data with older Voyager records stored in NASA archives. Researchers at the Harvard-Smithsonian Center for Astrophysics even examined historical signal patterns to see if similar events had occurred before. Nothing matched. The anomaly was new, and that is when curiosity started spreading through the mission team. Because Voyager's signal has traveled through space for billions of miles, and space itself is not empty. Interstellar space contains magnetic fields, cosmic radiation, charged particles drifting between stars. Data from Voyager's own plasma instruments has shown that the environment beyond the heliosphere is far more active than scientists once thought. Some researchers began wondering whether the signal might be interacting with something in that environment. Perhaps turbulence in the interstellar magnetic field was altering the transmission. Perhaps charged particles were interfering with Voyager's antenna. The idea sounded reasonable. But when scientists analyzed the signal more closely, they noticed something strange. The distortion did not look random. Random noise produces chaotic patterns. But the Voyager anomaly seemed structured, almost like a repeating sequence embedded inside the telemetry. That detail made engineers pause. Because Voyager was never programmed to transmit such patterns, the spacecraft's computers are extremely simple by modern standards. They cannot generate complex new data on their own. They only report measurements from instruments and basic engineering status. So if the pattern did not come from the spacecraft's software, where did it come from? That question sent researchers digging through decades of Voyager mission documentation, original engineering manuals from the Jet Propulsion Laboratory, old telemetry decoding charts, signal processing records from the Deep Space Network. They examined everything. One possible explanation involved Voyager's attitude control system. The spacecraft constantly adjusts its orientation so its antenna points toward Earth. If the orientation data became corrupted, the telemetry packets could appear scrambled, even though the spacecraft remained healthy. But when engineers compared the orientation data with star tracking measurements, Voyager's position looked perfectly stable. Another theory suggested the problem might come from Voyager's onboard flight data system. That system acts like the spacecraft's memory. If part of it began malfunctioning, it could send incorrect information even while other instruments continued working. Yet diagnostics from Voyager's subsystems showed no obvious failure. Everything appeared to be operating normally, which left one final possibility. The signal itself might be changing during its journey back to Earth. Radio signals traveling through space can be affected by plasma fields and magnetic turbulence. Astronomers studying pulsars often see similar distortions when signals pass through dense interstellar regions. To test this idea, researchers compared Voyager's signal with data gathered from other radio observatories. Historical measurements from the Arecibo Observatory provided valuable reference points. Observations from the Green Bank Telescope also helped analyze the structure of interstellar radio interference. But once again, the results created more questions than answers. Because the distortion inside Voyager's signal did not behave like normal cosmic interference, it appeared too organized, too consistent, almost like the signal itself was carrying something extra, something that Voyager was never supposed to send. And the deeper scientists looked into that strange signal, the more one uncomfortable thought began to surface. What if the anomaly was not caused by the spacecraft at all? What if the signal had interacted with something out there in interstellar space, something we do not fully understand yet? The idea that something might be affecting Voyager's signal out there in interstellar space sounds dramatic at first, but the truth is, the region beyond our solar system is far stranger than scientists once believed. For decades, people imagined the space between stars as a quiet vacuum, empty darkness where nothing happens. But Voyager changed that idea. When the spacecraft crossed the heliopause in 2012, it became the first human-made object to enter interstellar space. That boundary marks the edge of the sun's protective bubble. Inside that bubble, solar wind from our star dominates the environment. Outside it, the influence of the galaxy takes over. Voyager's instruments immediately started detecting something surprising. The density of plasma in interstellar space was higher than expected. Magnetic fields were stronger than models predicted. Even the flow of cosmic rays looked different from what scientists had imagined. These discoveries were confirmed by careful analysis of Voyager 1 telemetry at NASA's Jet Propulsion Laboratory. The results were later compared with cosmic ray observations from missions studying deep space radiation. All of this told researchers something important. Interstellar space is not quiet. It is active. Charged particles move through it. Magnetic waves ripple across it. Regions of plasma shift slowly over time, like invisible weather systems drifting through the galaxy. And Voyager is moving through all of it. Imagine a tiny radio transmitter drifting through a storm you cannot see. Now imagine that transmitter sending a signal back to Earth across 24 billion kilometers of turbulent space. Under those conditions, strange distortions might appear in the signal. That explanation became one of the leading theories inside the Voyager mission team. Engineers began examining the spacecraft's signal frequency very carefully. Voyager communicates using a narrow-band radio transmission designed to remain stable across enormous distances. The Deep Space Network listens for that signal constantly. Massive antennas in California, Spain, and Australia take turns receiving Voyager's transmissions as the Earth rotates. Each antenna collects tiny fragments of the signal and sends them to mission control, where powerful computers reconstruct the data stream. Normally, the signal is incredibly stable, but during the anomaly, the signal contained subtle irregularities. Some packets of telemetry arrived correctly, others appeared scrambled. Yet the spacecraft itself continued sending data as if nothing were wrong. Researchers began comparing these signals with other deep space radio sources. Observations from the Green Bank Observatory and archival studies from Arecibo legacy data provided valuable comparisons. Radio astronomers know that signals traveling through plasma can scatter in unusual ways. Pulsars, for example, often show distorted pulses when their radio waves pass through turbulent regions of interstellar gas. But Voyager's signal looked different. The pattern did not behave like random scattering. It looked almost structured, as if something inside the signal was repeating. That detail caught the attention of several scientists studying signal processing and astrophysics. At the Harvard-Smithsonian Center for Astrophysics, researchers who specialize in radio astronomy began examining the anomaly as well. Their goal was simple: determine whether the pattern could be explained by known astrophysical effects. One possibility involved magnetic field turbulence. The galaxy's magnetic field is not uniform. It twists and bends around clouds of interstellar gas. If Voyager's signal passed through one of these regions, it might experience distortions that look unusual. Another idea involved plasma waves detected by Voyager's own instruments. The spacecraft carries sensors designed to measure oscillations in interstellar plasma. In fact, those instruments once detected faint vibrations caused by a distant stellar explosion. The shock wave from that explosion traveled through the galaxy and reached Voyager years later. That event proved something remarkable. Signals and disturbances can travel enormous distances through the interstellar medium, which means Voyager's radio transmission is also traveling through that environment. If the signal crossed a region of unusually dense plasma or strong magnetic turbulence, it could change shape in subtle ways. Still, when scientists compared the data carefully, one thing continued bothering them. The anomaly appeared too consistent. Random interference should create chaotic distortions, but Voyager's strange signal seemed to carry repeating elements, almost like a pattern embedded in the telemetry stream. The spacecraft's onboard computer should not be able to generate anything like that. Voyager's systems are extremely simple. The software has not changed in decades. The flight data system was designed to send straightforward engineering measurements, temperatures, voltages, instrument readings, nothing more. Yet inside the anomaly, engineers noticed segments that did not match any known telemetry format. Some packets appeared shifted. Others contained values outside normal ranges. Yet the spacecraft itself continued functioning normally. Power levels remained steady. The antenna stayed locked on Earth. Cosmic ray detectors still reported data. That contradiction made the situation even stranger. If the spacecraft systems were failing, the engineering telemetry would show clear warning signs. But Voyager looked healthy, which raised a quiet possibility that nobody at Mission Control wanted to say out loud too quickly. What if the anomaly was not a failure at all? What if the signal itself had interacted with something during its journey back to Earth? Because Voyager's transmission travels through billions of kilometers of space filled with invisible forces, magnetic fields from distant stars, charged particles moving through the Milky Way, shock waves from ancient supernova explosions. And the deeper scientists looked into the signal anomaly, the more one unsettling idea began circulating among researchers. Voyager might be showing us something about interstellar space that we have never seen before, something hidden in the darkness between the stars. And if that idea turns out to be correct, then the strange signal from Voyager is not just a spacecraft glitch. It could be a clue about what really exists in the deep space environment beyond the solar system. And that realization changed the entire direction of the investigation. Because instead of asking what went wrong with Voyager, scientists began asking what Voyager might be discovering out there right now. The moment scientists began considering that possibility, the investigation changed completely. Instead of treating the Voyager signal anomaly as a simple spacecraft glitch, researchers started examining the deep space environment around the probe itself. Because Voyager is not just drifting through emptiness, it is moving through the interstellar medium. That region between stars contains thin clouds of charged particles, faint magnetic fields, and shock waves left behind by ancient stellar explosions. Most of the time, these features are extremely difficult to detect from Earth. But Voyager is physically inside that environment, and its instruments are measuring it in real time. When Voyager 1 crossed the heliopause in 2012, NASA scientists realized something incredible. Humanity had finally placed a scientific instrument in interstellar space. Everything the spacecraft measured beyond that boundary was new territory. Voyager's plasma wave instrument began detecting faint vibrations in the surrounding plasma. These vibrations allowed scientists to estimate the density of particles between stars. What they found surprised everyone. Interstellar space was denser than expected. It was not empty at all. Instead, it behaved more like a thin ocean of charged particles threaded with magnetic fields. Data from Voyager 1 telemetry showed that these magnetic fields remained aligned with the structure of our solar system even after the spacecraft crossed the heliopause. That was strange. Many models predicted that the interstellar magnetic field would be oriented differently from the solar magnetic field. Yet the transition appeared smoother than expected. Researchers at NASA's Jet Propulsion Laboratory analyzed the magnetic field readings carefully. When those readings were compared with models developed at the Harvard-Smithsonian Center for Astrophysics, the results suggested that our solar system might be moving through a complex region of interstellar space, almost like a current flowing through a larger galactic environment. Now imagine Voyager's radio signal traveling through that environment, a narrow beam of radio energy leaving the spacecraft and spreading outward across billions of kilometers. As that signal travels toward Earth, it passes through plasma waves, magnetic turbulence, and drifting particles. Most of the time, these interactions are too weak to cause noticeable distortion. But if Voyager happens to cross a region where those forces become stronger, something interesting could happen. the signal might change shape. Tiny delays could appear in the data packets. Segments of the transmission might scatter slightly before reaching Earth. Radio astronomers have seen similar effects when studying distant pulsars. Pulsars send incredibly precise radio pulses across the galaxy. When those signals pass through turbulent interstellar clouds, the pulses sometimes arrive stretched or distorted. Researchers studying pulsars often use this effect to map the structure of interstellar plasma. Voyager's signal might be revealing something similar. Except in this case, the spacecraft is not millions of light years away. It is only about 24 billion kilometers from Earth, close enough that scientists can study its telemetry in incredible detail. Engineers working with the Deep Space Network began analyzing the frequency stability of Voyager's transmission. The spacecraft communicates using the X-band radio frequency, a highly stable signal designed for long-distance communication. If something in interstellar space altered the signal, the effect should appear as tiny variations in frequency or phase. To investigate this possibility, the mission team compared Voyager's signal with reference measurements from Earth-based radio observatories. Historical data from Arecibo legacy records provided valuable comparisons. Additional observations from the Green Bank telescope helped analyze how radio waves behave when traveling through plasma-rich regions of space. But the results did not fully match typical interstellar scattering, which meant the anomaly might involve something happening directly inside Voyager's communication system. That brought scientists back to the spacecraft itself. Voyager's flight data system was built in the early 1970s using extremely simple memory circuits. The system stores telemetry data before sending it to the transmitter. If one portion of that memory becomes corrupted, the data stream might appear scrambled, even while the spacecraft continues operating normally. Radiation is a known cause of such problems. Cosmic rays traveling through interstellar space can strike electronic components and flip individual bits inside memory circuits. Normally, these errors appear random, but sometimes they can produce repeating distortions if a specific memory address becomes damaged. Engineers at the Jet Propulsion Laboratory began reviewing Voyager's onboard computer architecture in detail. The flight data system contains several sections responsible for formatting telemetry. One of those sections stores instructions that organize instrument readings into digital packets. If a small piece of that memory became corrupted, it could explain why Voyager continued sending signals while the data inside those signals looked unusual. The investigation soon revealed something fascinating. The strange telemetry pattern matched the structure of Voyager's data formatting system, but the instructions inside the memory appeared partially scrambled, which meant the spacecraft was likely operating with a damaged section of memory. Yet here is where the story becomes remarkable. Voyager is still working despite that damage. Engineers at Mission Control realized they might be able to work around the problem. By sending carefully designed commands through the Deep Space Network, they could redirect parts of Voyager's software to bypass the damaged memory area. This is incredibly difficult. Remember that the signal takes more than 22 hours to reach the spacecraft. Then another 22 hours for Voyager's response to return to Earth. Every command requires almost 2 full days before engineers know whether it worked. Despite that challenge, the Voyager team began testing solutions. Commands were transmitted across billions of kilometers of space. When the spacecraft responded, the signal looked slightly cleaner. Not perfect, but improved. That small improvement told scientists something encouraging. Voyager was still alive, still capable of communicating, still exploring the frontier of interstellar space. And yet, one question continued to echo through the investigation. If Voyager's signal anomaly was caused by memory corruption, what caused that corruption in the first place? Because the spacecraft had been traveling through interstellar space for more than a decade before the problem appeared, which means something may have changed in the environment around it, something powerful enough to affect the electronics of a probe drifting far beyond the solar system. And if that is true, then Voyager may have just encountered a region of deep space unlike anything we have studied before. The idea that Voyager may have encountered a new region of deep space changed the entire tone of the investigation. Because Voyager is not just another spacecraft. It is humanity's farthest explorer. No other probe has traveled this far from Earth. No other instrument is sending real-time data from the space between stars. That makes Voyager incredibly valuable for one simple reason. It is the only machine we have out there. So when something strange happens to its signal, scientists pay very close attention. At NASA's Jet Propulsion Laboratory, the team responsible for Voyager began looking at the spacecraft's recent trajectory. The probe is moving through the outer edge of a region known as the local interstellar cloud. This cloud is a vast area of gas and plasma drifting through our part of the Milky Way. It is incredibly thin compared to anything we experience on Earth, but on cosmic scales, it is significant. Our entire solar system is currently moving through this cloud as it orbits the center of the galaxy. Voyager reached the outer boundary of the Sun's influence just as it began entering this environment. That timing is important, because the local interstellar cloud contains fluctuations in plasma density and magnetic turbulence, regions where charged particles concentrate, regions where shock waves from distant stellar explosions ripple through space. Voyager's plasma wave instrument has detected some of these disturbances before. In fact, one of the most fascinating discoveries came when the spacecraft detected vibrations from a supernova shockwave. That shockwave originated from a star that exploded long ago. The blast traveled across interstellar space for years before reaching Voyager. When it finally passed the spacecraft, the plasma instruments recorded the disturbance as faint oscillations in the surrounding particles. Scientists studying the data realized something incredible. Voyager had just detected the echo of a stellar explosion happening light years away. That event proved that interstellar space is not quiet. It carries the fingerprints of cosmic events happening across the galaxy. Now imagine Voyager moving through that environment every day, traveling nearly 17 kilometers per second through invisible currents of plasma and magnetic energy. If the spacecraft encountered a particularly intense region of cosmic radiation, it could affect the electronics inside the probe. Cosmic rays are powerful particles that travel across the galaxy at nearly the speed of light. When they strike spacecraft electronics, they can cause something called a single event upset. That means a single particle can flip a bit of memory inside a computer. On modern spacecraft, protective systems detect and correct these errors automatically. But Voyager was built in the 1970s. Its computers are incredibly simple. They do not contain modern error correction systems. So when a cosmic ray hits the wrong circuit, the effect can linger. Engineers analyzing Voyager's flight data system realized that this might be exactly what happened. A high-energy particle could have struck the memory responsible for formatting telemetry data. If that memory became corrupted, Voyager would continue transmitting signals, but the data structure would appear scrambled. That explanation fit many aspects of the anomaly. But there was still something intriguing about the timing. The error appeared shortly after Voyager entered a region where cosmic ray intensity increased. Measurements from Voyager's cosmic ray subsystem showed that the number of high-energy particles hitting the spacecraft had been rising steadily since it crossed the heliopause. That makes sense. Inside the heliosphere, the Sun's magnetic field shields the solar system from many cosmic rays. Once Voyager moved beyond that protective bubble, the full force of galactic radiation became visible. In a way, Voyager left the safe harbor of the solar system and entered the open ocean of the galaxy. And out there, the radiation environment is far more intense. Researchers studying cosmic radiation have long predicted that spacecraft electronics may behave differently once they enter interstellar space. Voyager may now be proving that prediction. Yet even this explanation leads to another fascinating realization. Voyager is still functioning after nearly 50 years in space. Its power comes from radioisotope thermoelectric generators that slowly convert heat from decaying plutonium into electricity. Those generators continue producing enough energy to run a handful of instruments and the communication system. Every year, the power level drops slightly. Engineers must carefully choose which instruments remain active. Yet the spacecraft keeps going, still sending signals, still measuring the environment around it, still acting as a tiny messenger drifting between stars. The Deep Space Network continues listening. Massive radio antennas rotate slowly across the sky, tracking Voyager as Earth spins beneath them. The signal arriving at those antennas is incredibly faint. By the time Voyager's transmission reaches Earth, the power is less than a billionth of a watt. Detecting it requires extremely sensitive receivers and powerful signal processing systems. But the message still arrives, and inside that faint signal lies one of the most remarkable scientific stories ever told. A machine built nearly half a century ago is exploring a region no human has ever seen. And sometimes that machine sends back clues that make scientists stop and think. Clues about how the interstellar medium behaves. Clues about cosmic radiation. Clues about the forces shaping our galaxy. The strange Voyager signal may have started as a technical puzzle, but it also reminds us of something much bigger. We have placed a tiny piece of humanity in the vast darkness between stars, and that tiny machine is still talking, still reporting what it finds, still revealing the secrets of deep space. But there is one final question that continues to fascinate astronomers and engineers watching Voyager's signal. Because if cosmic radiation can alter the spacecraft's memory once, it might happen again. And next time, the anomaly might not just scramble telemetry. It could reveal something even stranger hidden in the deep space environment Voyager is traveling through. Something that no spacecraft has ever encountered before. The longer the Voyager investigation continued, the clearer one thing became. The strange signal was not just a small technical glitch. It was a reminder of how fragile machines become when they travel far beyond the protection of Earth. Voyager was never meant to last this long. When engineers at NASA's Jet Propulsion Laboratory designed the spacecraft in the early 1970s, the original mission timeline was only a few years. The goal was simple: fly past Jupiter and Saturn, collect as much data as possible, and transmit those discoveries back to Earth. Nobody expected the spacecraft to keep operating for nearly half a century. Yet Voyager did more than survive. It kept exploring. After leaving Saturn behind, the spacecraft continued its long journey toward the outer edge of the solar system. For decades, it moved quietly through the distant regions beyond Neptune, carrying instruments that continued measuring magnetic fields, cosmic rays, and solar wind particles. Then something historic happened. Voyager reached the heliopause. That invisible boundary marks the edge of the sun's influence. Inside the heliosphere, the solar wind dominates space. Outside it, the environment belongs to the galaxy itself. When Voyager crossed that boundary in 2012, the spacecraft became the first human-made object to enter interstellar space. Suddenly, the mission had entered a completely new phase. Instead of studying planets, Voyager was now studying the deep space environment between stars. And that environment turned out to be far more active than scientists once believed. Voyager's instruments began detecting changes in plasma density. The magnetic field around the spacecraft behaved differently than expected. Cosmic ray detectors started measuring higher levels of high-energy radiation. Each new reading gave scientists a rare glimpse into a part of the universe we had never explored before. For astrophysicists studying the structure of the Milky Way, this was incredibly valuable data. The interstellar medium is the vast mixture of gas, dust, and charged particles filling the space between stars. It shapes how galaxies evolve. It carries shock waves from exploding stars. It forms the raw material that eventually collapses into new solar systems. but studying it directly is extremely difficult. Most of what we know comes from distant observations using powerful telescopes. Voyager changed that. For the first time, scientists had a probe physically moving through that environment, which meant that every strange signal, every unexpected reading might reveal something important. That is why the recent Voyager signal anomaly attracted so much attention. Because the spacecraft is operating in conditions no probe has experienced before, deep space radiation constantly bombards its electronics. Charged particles move past it like invisible currents. Magnetic turbulence ripples through the region around it. All of these factors can influence spacecraft systems in subtle ways. Engineers studying the anomaly eventually confirmed that a portion of Voyager's flight data system memory had been corrupted. But the deeper question remained: what caused the corruption? The leading explanation involves cosmic rays. Cosmic rays are among the most energetic particles in the universe. They are produced by violent astrophysical events, like supernova explosions and the powerful magnetic fields surrounding neutron stars. When these particles travel through space, they can strike spacecraft electronics with tremendous energy. Inside the heliosphere, the sun's magnetic field deflects many of these particles. But Voyager is now outside that protective bubble. It is exposed directly to the radiation environment of the galaxy. Measurements from Voyager's cosmic ray subsystem show that the number of high-energy particles hitting the spacecraft has increased dramatically since it entered interstellar space. Each one of those particles carries enough energy to interfere with electronic circuits, and occasionally, one of them strikes the wrong component. When that happens, a memory bit flips. A tiny digital change that can scramble instructions inside a computer system. In Voyager's case, that single change was enough to distort the telemetry data being transmitted back to Earth. Yet the spacecraft itself kept working. That fact impressed many engineers working on the mission. Voyager systems were designed with incredible simplicity and redundancy. Even with partial memory corruption, the spacecraft continued functioning. It still pointed its antenna toward Earth. It still transmitted data through the deep space network. And it still reported readings from its instruments measuring cosmic rays and magnetic fields. Which means Voyager remains our most distant scientific outpost. Right now, as this signal travels back to Earth, the spacecraft is still moving outward through the galaxy. Every second, it travels nearly 17 kilometers farther from the Sunday. That might not sound fast, but over time, it adds up. In 1 year, Voyager travels more than 500 million kilometers. Over the course of decades, that distance becomes enormous. Eventually, the spacecraft will pass beyond the local interstellar cloud and enter a new region of the galaxy. What it encounters there is still unknown, and that is part of what makes Voyager so fascinating, because it is exploring a frontier we barely understand. The strange signal anomaly reminded scientists that deep space is not as predictable as we once thought. The environment beyond our solar system contains forces capable of altering electronics, bending magnetic fields, and reshaping plasma structures across enormous distances. Voyager is moving through all of it, quietly, slowly, sending back faint radio whispers across billions of kilometers. Each signal reaching Earth carries a tiny piece of information about the environment between stars. Most of the time, that information looks normal. But sometimes, like during the recent anomaly, the signal behaves in ways that make scientists pause. And those moments are valuable, because every unexpected signal can teach us something new about the universe. Something hidden in the darkness beyond our solar system. Something Voyager is discovering long before any human spacecraft will ever reach that far. And as long as the probe continues transmitting, astronomers and engineers will keep listening carefully, waiting for the next whisper from the deepest edge of human exploration. For scientists watching Voyager's signal, every transmission now feels like a fragile lifeline. Because the spacecraft is getting old, very old. Voyager, launched in 1977. The technology inside it was already considered advanced for its time, but compared to modern spacecraft systems, it is extremely simple. Its memory capacity is tiny. Its processors run slowly. Its electronics were never expected to survive for decades in deep space radiation. Yet somehow it continues, still sending signals, still whispering data across billions of kilometers of empty space. That persistence has made Voyager one of the most remarkable scientific missions in the history of NASA. But it also means the spacecraft is now operating on borrowed time. Every year, the power supply drops slightly. Voyager's electricity comes from radioisotope thermoelectric generators. These devices convert heat from decaying plutonium into electrical energy. They contain no moving parts, which is why they can last so long. But the fuel slowly loses strength. Each year, the spacecraft produces a little less power. Engineers at the Jet Propulsion Laboratory must constantly decide which instruments stay on and which must be shut down to conserve energy. Several instruments have already been turned off. Others remain active because they provide unique information about the environment beyond the heliosphere. The cosmic ray subsystem is still measuring high-energy particles drifting through interstellar space. The magnetometer continues monitoring the invisible magnetic field surrounding the spacecraft. The plasma wave instrument listens to faint vibrations in the interstellar plasma. Together, these instruments tell scientists how the galaxy behaves in the region surrounding our solar system. And that information is incredibly valuable, because no telescope on Earth can measure those conditions directly. Voyager is our only messenger from that region of space, which is why the strange signal anomaly created such a wave of curiosity among astronomers, astrophysicists, and space engineers. It reminded everyone that Voyager is operating in an environment where unexpected things can happen. Deep space radiation, magnetic turbulence, plasma waves moving across the galaxy. Any of these forces can influence the spacecraft. And sometimes they reveal themselves through subtle clues hidden inside the telemetry. For the Voyager team, every new signal becomes part of a larger puzzle. Engineers decode the data using software that interprets Voyager's telemetry formats. These formats were designed decades ago and carefully preserved in mission archives. When the signal anomaly appeared, scientists compared the corrupted data with historical Voyager telemetry stored in NASA records. They also reviewed signal processing measurements gathered by the Deep Space Network antennas. Those antennas are among the most powerful radio listening systems ever built. Each dish measures more than 70 meters across. When they focus on Voyager's signal, they are detecting radio energy weaker than the power used by a digital watch. Yet with advanced receivers and sophisticated filtering techniques, the Deep Space Network can still hear Voyager's whisper from interstellar space. That ability allows scientists to monitor even tiny changes in the signal. And sometimes, those changes reveal fascinating insights about the environment surrounding the spacecraft. Radio astronomers studying the Voyager anomaly began comparing the signal with observations from other radio sources across the galaxy. Signals from pulsars, quasars, and distant galaxies often experience distortions when passing through turbulent plasma clouds. Those distortions help researchers map the structure of the interstellar medium. If Voyager's signal is experiencing similar effects, it might reveal new information about the region the spacecraft is currently crossing. In that sense, even the anomaly itself becomes scientific data, a clue about what lies beyond the edge of the solar system. One of the most intriguing possibilities involves the boundary between the local interstellar cloud and neighboring interstellar regions. Astronomers believe our solar system is moving through a cluster of interstellar clouds with slightly different densities and magnetic structures. Voyager may be approaching the edge of one of those clouds. If that transition occurs, the spacecraft could encounter sudden changes in plasma density and magnetic turbulence. Such changes might increase the intensity of cosmic rays striking the probe. They could also influence how radio signals travel through the surrounding plasma. If Voyager's signal is being distorted by such conditions, it could provide the first direct evidence of those boundaries. That would be an incredible discovery, because understanding the structure of the interstellar medium helps scientists learn how stars form, how supernova shockwaves travel across the galaxy, and how cosmic radiation spreads through space. Voyager may be revealing the fine details of that environment simply by continuing to transmit. And that brings us back to the strange signal that started this investigation. What first looked like a troubling glitch turned out to be a reminder of how extraordinary this mission really is. A spacecraft built in the 20th century is now drifting through the galaxy. It has traveled farther than any object humans have ever created. It has survived planetary flybys, solar storms, deep space radiation, and the cold emptiness beyond the heliosphere. And it is still talking to us, still sending data, still revealing secrets about the space between stars. The anomaly inside Voyager's signal may have been caused by cosmic radiation flipping a tiny piece of memory. But the bigger story is what that moment revealed. It reminded us that Voyager is now operating in the most extreme environment any spacecraft has ever explored. And every signal that reaches Earth carries a new piece of the puzzle, a new glimpse into the deep space environment surrounding our solar system. As long as Voyager continues transmitting, scientists will keep listening, because somewhere out there, far beyond the orbit of every planet, the spacecraft is still moving forward, still crossing new regions of interstellar space, still discovering things we have never seen before. And every whisper from that distant probe brings us closer to understanding the vast galaxy we live in. The deeper scientists studied the strange Voyager signal, the more the story began to reveal something bigger than a simple spacecraft malfunction. Because Voyager is no longer just a probe. It has become a moving laboratory inside one of the least understood regions of our galaxy, the interstellar medium. For decades, astronomers tried to understand that region using powerful telescopes. Instruments at places like the Keck Observatory and radio measurements collected by the Arecibo Observatory allowed researchers to analyze distant clouds of gas drifting between stars. But those observations always had one limitation. They were indirect. Scientists could only observe interstellar space from far away. Voyager changed that. For the first time in human history, a spacecraft is physically inside that environment, which means every signal coming from Voyager contains real data about conditions between stars. And sometimes that data behaves in ways that surprise even experienced astrophysicists. After the anomaly appeared in Voyager's telemetry, the investigation expanded beyond engineering teams at NASA. Radio astronomers began analyzing the signal structure more closely. Astrophysicists studying cosmic radiation compared Voyager's measurements with data collected from observatories around the world. Researchers at the Harvard-Smithsonian Center for Astrophysics examined whether large-scale structures in the Milky Way could influence signals traveling through the interstellar medium. The reason for this wider investigation is simple. Radio waves traveling across enormous distances are sensitive to the environment they pass through. Even small changes in plasma density can bend or scatter those signals. Magnetic turbulence can cause subtle shifts in frequency, and shock waves from distant supernova explosions can create disturbances that ripple across light years of space. Voyager's signal must travel through all of these conditions before reaching Earth. The spacecraft transmits using a narrow beam aimed directly toward our planet. But that beam spreads slightly as it travels. By the time the signal arrives at Earth, it has expanded across millions of kilometers. Only a tiny fraction of that energy is captured by the Deep Space Network antennas. Yet inside that faint signal lies a wealth of information, and sometimes unexpected clues. For scientists studying deep space exploration, this is exactly the kind of puzzle that leads to new discoveries. Because every anomaly forces researchers to look deeper, to ask new questions, to examine data in ways they had not considered before. One of the most fascinating aspects of the Voyager signal anomaly is how it demonstrates the resilience of the spacecraft itself. Even after nearly 50 years in space, Voyager continues operating with remarkable reliability. The probe still maintains communication with Earth. It still reports the intensity of cosmic radiation striking its detectors. It still measures magnetic fields drifting through interstellar space. And most importantly, it still carries humanity's message beyond the solar system. Attached to Voyager's side is the famous Golden Record, a phonograph disc containing sounds and images from Earth, greetings in multiple languages, music from different cultures, even the sound of waves crashing on a beach. The record was designed as a time capsule, a message to any civilization that might someday discover the spacecraft drifting through the galaxy. But in reality, the Golden Record serves another purpose. It reminds us why Voyager matters. Because this tiny machine represents humanity's first step into the ocean of interstellar space. And the strange signal anomaly shows how unpredictable that ocean can be. The deeper Voyager travels into the galaxy, the more unknown forces it encounters. Cosmic radiation from ancient supernova explosions, magnetic waves drifting through plasma clouds, particles accelerated by distant stellar events. All of these forces shape the environment around the spacecraft. Most of the time they remain invisible, but occasionally they leave fingerprints inside the telemetry. Little distortions that catch the attention of scientists listening carefully to Voyager's signal. Moments like these remind us that exploration rarely follows a straight path. Sometimes discoveries appear in the form of unexpected signals, unexpected patterns, unexpected questions. The Voyager anomaly is one of those moments. It forced researchers to revisit decades of spacecraft engineering data. It sparked new conversations about the behavior of cosmic radiation beyond the heliosphere. And it reminded scientists that the interstellar medium is far more dynamic than once believed. Yet perhaps the most incredible part of this story is that Voyager is still moving. Right now, while this signal travels across space, the spacecraft continues its silent journey away from the Sunday. Every second, it travels another 17 kilometers. Every hour, it moves farther into the galaxy. And every day, it enters a region of space no human technology has explored before. Eventually, the spacecraft will lose enough power that its transmitters shut down. That moment will come sometime within the next decade. When it does, Voyager will finally fall silent. But its journey will not end. The probe will continue drifting through the Milky Way for millions of years, passing near distant stars, carrying its golden record across the galaxy. And somewhere out there in the darkness, long after its signal fades, Voyager will remain a silent witness to humanity's first attempt to reach the stars. But until that day arrives, scientists will keep listening. Because every signal that reaches Earth could reveal something new, something strange, something hidden in the vast environment between stars. And sometimes, a simple anomaly in a radio signal becomes the beginning of a much bigger discovery. One that reminds us how little we truly know about the deep space frontier just beyond our solar system. The story of Voyager is not just about a spacecraft. It is about the moment humanity began listening to the universe from the inside. By the time the Voyager signal anomaly had been studied for weeks, something interesting happened inside the scientific community. The story began spreading, not just inside NASA, but across astronomy labs, space science departments, and astrophysics research groups around the world. Because Voyager is not an ordinary spacecraft. It is the farthest human-made object in history. And when something strange appears in the signal from the edge of interstellar space, scientists everywhere want to understand it. Researchers studying deep space communication began revisiting old Voyager signal records. Decades of telemetry stored inside NASA archives were analyzed again. Signal patterns from the 1980s, data streams from the 1990s, even transmissions recorded when Voyager was still inside the outer solar system near Neptune. The goal was simple: determine whether anything like this had ever happened before. Engineers at NASA's Jet Propulsion Laboratory compared the anomaly with historical Voyager telemetry formats. They examined how the spacecraft's flight data system organizes information before sending it through the transmitter. At the same time, astrophysicists studying the interstellar medium began asking a different question. Could the environment between stars actually influence spacecraft signals in ways we have never measured before? This question became surprisingly important because Voyager's signal travels through billions of kilometers of deep space before reaching Earth. Along that journey, the radio transmission passes through regions filled with cosmic radiation, interstellar plasma, and magnetic turbulence. Each of those forces can alter radio waves in subtle ways. Radio astronomers already see this effect when studying pulsars, which are rapidly spinning neutron stars that emit regular radio pulses across the galaxy. When those pulses pass through dense plasma clouds, they sometimes arrive distorted. The signal stretches slightly. The frequency shifts. The timing changes. Scientists studying those distortions can actually map the structure of the interstellar medium. So, researchers began asking an intriguing possibility. What if Voyager's signal was revealing similar distortions? What if the anomaly was not just an engineering problem, but a clue about the environment Voyager is traveling through right now? To explore this idea, scientists compared Voyager's radio signal with data from large radio telescopes. Observations from the Green Bank Observatory helped measure how radio waves behave when traveling through turbulent plasma regions. Historical radio studies from Arecibo Observatory legacy data also provided reference measurements for signal distortion across interstellar distances. The comparison revealed something fascinating. Voyager's signal did show signs of distortion consistent with plasma interactions, but the pattern still contained traces of corrupted telemetry structure, which meant the anomaly likely involved two different effects happening at the same time. First, cosmic radiation had damaged part of Voyager's onboard memory. Second, the signal traveling back to Earth was passing through an environment filled with plasma and magnetic turbulence. Together, those effects created a signal pattern that looked unusual. To engineers, it appeared like scrambled telemetry. To astrophysicists, it looked like a radio transmission interacting with the deep space environment. In other words, the strange Voyager signal may have been both a spacecraft glitch and a scientific discovery at the same time. And that possibility excited many researchers. Because Voyager is currently traveling through a region that has never been studied directly by any spacecraft before, the outer edge of the local interstellar cloud. This cloud is part of a larger structure called the local bubble, a huge cavity of hot gas surrounding our solar system. Astronomers believe the local bubble was created by ancient supernova explosions millions of years ago. Those explosions pushed gas outward, leaving behind a giant region of lower density plasma. Our solar system sits inside this bubble today, but Voyager is moving toward the boundary where that environment begins to change. If the spacecraft is approaching a transition zone between interstellar regions, scientists might expect unusual plasma conditions, fluctuating magnetic fields, increased cosmic radiation, dense pockets of charged particles. Any of these could influence radio signals traveling across billions of kilometers, which means Voyager might be revealing something scientists have wanted to measure for decades: the structure of interstellar space near our solar system. This is why the Voyager mission continues attracting attention across the scientific world. Even after nearly 50 years, the spacecraft remains one of the most important tools for studying deep space exploration, cosmic radiation, and the environment beyond the heliosphere. And every signal from the probe contains valuable information, even the strange ones, especially the strange ones. because anomalies often lead to discoveries. Throughout the history of astronomy, some of the most important breakthroughs began with signals that looked confusing at first. Unexpected radio pulses, unusual spectral lines, strange patterns hidden inside astronomical data. Voyager's signal anomaly fits that pattern perfectly. At first it looked like a technical failure, but the deeper scientists investigated it, the more it revealed about the environment beyond our solar system. And the story may not be finished yet, because Voyager is still moving, still traveling outward through the galaxy, still crossing regions of space that no spacecraft has ever explored before. Which means the next strange signal might arrive tomorrow, or next month, or years from now. And somewhere out there, in the darkness between stars, the tiny spacecraft continues its silent journey, still transmitting, still exploring, still sending whispers from the deepest frontier of human exploration. As the Voyager investigation continued, something deeper began to emerge from the data. The strange signal was not just about a spacecraft problem. It was about the environment surrounding the spacecraft. Because Voyager is currently moving through a region that scientists have wanted to study for decades but could never reach before. The boundary between the solar system and the galaxy. This boundary is not a wall. It is more like a shifting frontier. Inside the heliosphere, our sun dominates the space environment. The solar wind pushes outward, creating a giant protective bubble that shields planets from a large portion of cosmic radiation. But beyond that bubble lies a different world. The interstellar medium. That environment is shaped by the magnetic field of the Milky Way and by shock waves created when stars explode. Voyager is now traveling directly through that region, which means every signal from the spacecraft is also a report about the deep space environment beyond our solar system. When scientists looked again at Voyager's cosmic ray data, they noticed something interesting. The intensity of high-energy particles around the spacecraft has been slowly rising, not suddenly, gradually. That increase suggests Voyager is moving into a region where cosmic radiation becomes stronger. Researchers studying galactic radiation believe this could mean the spacecraft is approaching a boundary between interstellar clouds. These clouds are enormous structures of gas and plasma drifting through the Milky Way. Our solar system currently sits inside one called the local interstellar cloud, but nearby clouds have slightly different densities and magnetic properties. If Voyager crosses from one region into another, the environment around the spacecraft could change dramatically. Plasma density could shift, magnetic turbulence could increase, cosmic radiation could become more intense. All of these forces could influence both Voyager's instruments and the signal it sends back to Earth. For scientists studying deep space exploration, this is incredibly exciting, because until now, these boundaries have only been observed indirectly using telescopes. Voyager may be providing the first direct measurements from inside that transition zone. At NASA's Jet Propulsion Laboratory, engineers monitoring the spacecraft began looking for other signs that Voyager might be entering a new interstellar environment. Magnetic field data from the spacecraft's magnetometer showed subtle variations. The direction of the field changed slightly, not dramatically, but enough to suggest that Voyager may be approaching a region where the galactic magnetic structure becomes more complex. These variations were compared with models developed by astrophysicists studying the structure of the Milky Way. Some of those models predicted that the local interstellar cloud may have turbulent boundaries where magnetic fields twist and fold. If Voyager is moving toward one of those boundaries, the spacecraft could encounter regions where plasma density fluctuates rapidly. That environment would be very different from the relatively stable conditions Voyager experienced just after leaving the heliosphere. And those changing conditions could explain several unusual signals detected recently. For example, the plasma wave instrument aboard Voyager has occasionally detected faint oscillations in the surrounding particles. These oscillations behave like ripples in a cosmic ocean, They can be triggered by distant events, such as supernova shock waves, or by turbulence where interstellar clouds interact. When such waves pass Voyager, they create subtle vibrations in the plasma around the spacecraft. Those vibrations can influence radio transmissions passing through the same region, which means Voyager's signal might be acting like a probe inside the interstellar plasma environment. Every distortion in the signal could carry information about the structure of the medium surrounding the spacecraft. This is why the strange Voyager signal attracted so much attention. It may represent one of the first times humanity has observed how deep space conditions affect a spacecraft operating far beyond the solar system. And that realization changes how scientists think about interstellar exploration. Because Voyager is not just traveling through space. It is traveling through a complex cosmic environment shaped by forces that operate across the entire galaxy. Magnetic fields stretching thousands of light years. Radiation from exploding stars. Clouds of gas drifting between stellar systems. All of these elements form the interstellar medium, and Voyager is now inside it. For researchers studying NASA missions, deep space signals, cosmic radiation, and the edge of the solar system, this makes Voyager one of the most important scientific probes ever built, even today, nearly 50 years after launch. The spacecraft continues revealing new information about the galaxy, and sometimes that information arrives in unexpected ways. A distorted signal, a strange telemetry pattern, a ripple in the surrounding plasma. Each one becomes a clue, a small piece of a much larger puzzle, the puzzle of what lies beyond the protective bubble of our Sunday. And the more scientists study those clues, the more they realize something profound. The region just outside our solar system is far more active than we ever imagined. Voyager may only be a tiny machine drifting through that enormous environment, but every signal it sends back helps us understand the galaxy we live in. And somewhere out there, more than 24 billion kilometers away, the spacecraft continues its silent journey, still moving deeper into interstellar space, still exploring a frontier that humanity has barely begun to understand. The longer Voyager continues its journey, the more it begins to feel less like a spacecraft and more like a witness to a region of the universe that humans have never experienced before. Because the space beyond the heliosphere is not just another part of the solar system, it is the beginning of the galaxy. Everything Voyager encounters now belongs to the larger structure of the Milky Way. The particles striking its detectors were accelerated by events that happened light years away. The magnetic fields bending around the spacecraft were shaped by the rotation of our galaxy. Even the plasma drifting through this region may have originated from ancient stellar explosions. In other words, Voyager is now exploring the raw environment that fills the space between stars. This realization has changed how scientists think about the spacecraft's mission. Originally, Voyager was built to explore planets, but today it is exploring the deep space frontier beyond our solar system. And the strange signal anomaly reminded researchers of something important. Every spacecraft that eventually travels to another star system will face the same environment Voyager is experiencing right now. Cosmic radiation, interstellar plasma, magnetic turbulence moving across enormous distances. All of these forces influence spacecraft electronics, communication signals, and navigation systems, which means Voyager is acting like a pathfinder, a tiny scout traveling ahead of humanity's future interstellar missions. Engineers studying the Voyager anomaly began asking a new question. What can we learn from this spacecraft about surviving in deep space? The answer could influence how future probes are designed, because if cosmic radiation can corrupt memory systems in Voyager, then future spacecraft traveling beyond the heliosphere will need stronger protection, new electronics, better shielding, more advanced error correction systems. Voyager's experience may help engineers prepare for those challenges. But the spacecraft is also teaching scientists something equally important. The interstellar medium is dynamic. For many years, textbooks described interstellar space as mostly calm, a thin mixture of gas and dust slowly drifting between stars. Voyager has shown that description is incomplete. The environment beyond our solar system behaves more like a moving ocean. Plasma waves ripple across vast distances. Magnetic fields twist and interact. Cosmic radiation surges through the region like invisible storms. These forces constantly reshape the conditions Voyager experiences, and occasionally they leave fingerprints inside the signal that reaches Earth. That is why astronomers continue monitoring Voyager's transmissions so carefully. The Deep Space Network antennas never stop listening. Those massive dishes in California, Spain, and Australia track Voyager's signal as Earth rotates beneath the sky. When the spacecraft sends data, the signal travels for more than 22 hours before reaching Earth. That signal is incredibly faint. By the time it arrives, it carries less power than a whisper in a hurricane. Yet with sensitive receivers and advanced processing techniques, scientists can still reconstruct the telemetry. Inside that faint signal lies information about cosmic radiation levels, magnetic fields, and plasma vibrations surrounding the spacecraft. Each packet of data adds another piece to our understanding of the galaxy. And sometimes those packets contain surprises, like the strange signal anomaly that started this investigation. At first, it looked like a troubling glitch. But the deeper scientists looked, the more it revealed about the extreme conditions Voyager now faces. A spacecraft operating billions of kilometers from Earth, electronics exposed directly to galactic radiation, signals traveling through plasma currents that stretch across interstellar space. And yet the probe continues transmitting, still sending data, still exploring, still expanding humanity's understanding of the deep space environment beyond the solar system. But Voyager's journey is not endless. Eventually, its power will fade. Within the next decade, engineers expect the remaining instruments to shut down one by one as the spacecraft loses energy. When the final transmitter goes silent, Voyager will become a drifting artifact of human history. A silent probe traveling through the Milky Way for millions of years. But until that moment arrives, Voyager continues doing something extraordinary. It continues sending messages from the edge of human exploration. Each signal crossing billions of kilometers. Each transmission carrying clues about the interstellar medium, cosmic radiation, and the deep space frontier beyond our solar system. And sometimes, hidden inside those signals, scientists find strange patterns that remind us just how mysterious the universe still is. Because the farther Voyager travels from Earth, the more it begins to reveal about the galaxy we call home. And somewhere out there, in the darkness between stars, that small spacecraft continues moving forward, still listening, still transmitting, still telling the story of what exists beyond the edge of our solar system. For weeks, the investigation circled around the same question. What exactly happened to Voyager's signal? Engineers at NASA's Jet Propulsion Laboratory kept examining every piece of telemetry coming from the spacecraft. Radio astronomers studied the faint transmission captured by the Deep Space Network. Astrophysicists compared the anomaly with models of cosmic radiation and plasma turbulence in interstellar space. Slowly, the answer began to come into focus. The strange signal was not a message from something unknown. It was something far more revealing. A tiny scar inside the memory of a machine that had traveled farther than any human technology ever built. A single corrupted instruction inside Voyager's flight data system had changed the way the spacecraft organized its telemetry packets. That tiny digital shift made the signal look strange when it reached Earth. Yet the spacecraft itself was still operating normally, still measuring cosmic radiation, still detecting magnetic fields drifting through interstellar space, still pointing its antenna toward Earth with incredible precision. The anomaly was real, But it was not the end of the mission. In fact, it revealed something remarkable. Voyager had survived nearly 50 years of space exploration and was still functioning even after being struck by high-energy cosmic radiation in the depths of the galaxy. The spacecraft was doing exactly what it had been designed to do: endure, transmit, explore, and perhaps the most powerful part of this story is what Voyager represents today. It is no longer just a scientific instrument. It is humanity's most distant messenger. Right now, Voyager 1 is more than 24 billion kilometers from Earth. Its signal takes nearly a full day to reach us. The spacecraft moves farther into the galaxy every second. No human being has ever traveled that far. No other spacecraft has explored that region of space. Yet Voyager continues sending back whispers from the deep space frontier. Those whispers tell us about cosmic radiation drifting through the Milky Way. They reveal the invisible magnetic structure surrounding our solar system. They show us how the interstellar medium behaves far beyond the protective bubble of the Sunday. And sometimes, those whispers arrive with strange distortions that remind scientists just how extreme that environment truly is. The strange Voyager signal did not come from aliens. It did not come from a hidden object in deep space. It came from the brutal reality of the galaxy itself. High-energy particles moving across the universe struck a tiny spacecraft built decades ago and changed a few bits of memory. Yet even after that hit, Voyager kept working, still transmitting, still exploring, still carrying humanity's curiosity into the darkness between stars. And that might be the most inspiring part of this entire story. Because Voyager proves that human exploration does not end at the edge of the solar system. It continues outward, quietly, patiently, across distances so large they are difficult to imagine. Long after the spacecraft finally falls silent, it will keep drifting through the Milky Way. Millions of years from now, it may pass near distant stars, perhaps even through the outskirts of another planetary system. And attached to its side will still be the golden record, a small message from Earth traveling through the galaxy. A reminder that a civilization once looked up at the stars and decided to explore. For now, Voyager is still speaking, still sending signals across billions of kilometers of deep space. And every time those signals arrive at Earth, scientists listen carefully, because somewhere out there, at the edge of human exploration, the most distant spacecraft ever built is still telling us what the universe looks like beyond our solar system. If you want to keep exploring deep space discoveries like this, subscribe and continue with the next cosmic investigation.